I'm going to talk about CubeMap. So that stands for CubeSats for Monitoring Atmospheric Processes. It's a CubeSat mission, as the name suggests. So briefly, what I'm going to go through over these 15 minutes, it's going to be quite fast, quite a lot. I might eat up a bit of question time. I want to go through the mission context, give you the scientific rationale for the mission, describe the observation concept. I'll describe the scientific payload associated to that. I'll move you through the data, down to the data product with some example simulated data, a word on the platform, and then something we are currently on doing, which is a risk-scoping activity, and I'll give you a forward look. So let's start with the mission context. So it started quite a few years ago, 4 or 5, I can't remember, where ESA released its first program called at the time a Small Satellite Challenge, which have been rebranded as a Scout since then. So the idea was to enable some new mission implementing in an agile, fast way with some innovative instrumentation and a fairly small budget to enable some small-scale mission complementary to the large scientific mission. So when we look at that, we decided to go for it addressing atmospheric challenges. And we went through the full cycle, so from the initial proposal to down selection, to consolidation studies, to selection by the ACO, and we've been now implementing for about 18 months. The industrial prime is GomSpace in Denmark, so it's responsible for providing the platform, the mission operating center, the ground station network, and the launch. And we at Trial Space, we are responsible for scientific activities, so developing the scientific instrument, the simulators, and the payload data center. The current program is a 3-year implementation, needs to be fast, and the launch is planned for Q1 2025. So what is the scientific rationale? Very, very quickly. We're interested in studying processes in the middle atmosphere because the middle atmosphere is very sensitive to change and also drives the surface temperature and the near-term climate variability. So we have also feedback mechanisms which are largely uncertain in this region of the atmosphere. So that's what we're going to focus on to understand better processes. The other aspect we're focusing on is on the tropical region. The reason being that you have all mega cities in these regions. That means pollution emission, greenhouse gases emission, aerosols emission at the surface level, which due to the convective uplift make their way very quickly into the middle atmosphere and alter its composition. So that's really the generic scientific rationale. And with the scientific advisory group of the mission, which is listed on the slide, we looked at describing some specific mission objectives around that, which I will go through very quickly. The first one is about looking at water vapor. So currently, in terms of modeling, the lower stratosphere water vapor is there is no consistency. So there's still a problem there. So the idea is to provide more quantitative information about water vapor in this region to help improving model and validating them. The second objective is about ozone. So the ozone redistribution, the recovery on one side in the stratosphere, but also the impact of the lower stratospheric cooling and the way it redistributes ozone and the UV radiation reaching the surface and affecting bioreceptors. The third one is about greenhouse gases emissions, so methane, CO2, and nitrous oxide. The idea here is to provide an accurate vertical representation of the profile of the species in the UTLS and the stratosphere, so that combined with nadir sounder column information, you can get a better grasp of the lower troposphere, which is more coupled to surface emission and improved on local regional emission of greenhouse gases. The last one is about the UTS composition as a whole. We've focused on aerosols. I took a plot, for example, of the Asian tropos aerosol layer and the quantitative study of this type of aerosol profile. So that's the objective. So now let's see what system and sounding geometry we're using for this. So we're interested in the higher vertical resolution of the UTLS, which is very strongly structured. So not surprisingly, we're going to use limb sounding. We're also looking at region of the atmosphere at low pressure, where the collisional broadening is limited. Therefore, we need a high resolution spectrometer, and we need high accuracy. And the question here, how can we do that from a very small CubeSat platform? So the idea here is really in line with what Chris Boone has presented yesterday in the framework of the ACE-FTS mission. We use the sun as the third body in the system, which gives us a very strong background, so high SNR, the self-calibration aspect using exoatmospheric signals. But we have to account for this third body in the equation and the fact that we need to have a pointing at the right time, at the right place for the spacecraft. Another aspect of solar occultation limb sounding has already been mentioned, is the coverage, which is only 2 observations per orbit. So that means in terms of coverage, it has some implications. So let's look at that. As part of the mission implementation, we've developed the orbital simulator based on the ORCID software package to be able to simulate the observation. So that's what you can see on the top map as red dots. So observation point over a period of 1 month. Now, in terms of geographical resolution, the way we deal with it, we're interested in looking at processes over, we want a full coverage of the tropics and part of the subtropics over a month. The spatial resolution we need is in the range of the synoptic scale, so we choose a grid of 4 by 8 degree, and then what we do, we bin this observation into our reference grid to see whether we're able to get a full coverage map. So that's what you can see on the bottom one. The red square means we have no observation. So we have a fairly scarce coverage when we're using only one spacecraft. And that's where the CubeSat is an enabling technology here, because you can actually start thinking, as the previous speaker mentioned, about constellation. Now, if you take 3 spacecraft evenly distributed on the orbital plane, this is the type of coverage you get. In this case here, you get your full coverage, so 90-degree latitude ridge, which oscillates with season north-south. But you get your full coverage, and even better, you get more than one observation in most of the cells, which means you build redundancy, which is also quite important given the reliability of CubeSats. So that's what we're going for. It's a constellation of limb sounder occultation sounder. Now let's look at the scientific instrument we have on board. And I'll take you through these using simulated data using our simulator. So the first system we have on board is a solar disk imager, which is essentially needed for recovering the pointing. So what happens is that during the occultation, the instrument will take an image every second of what is in the field of view, and hopefully in the field of view we should have the sun disk that we will follow throughout the occultation as the occultation happens. And from that, we'll be able to recover what are the tangent height being probed as a function of time and get the pointing, the sort of measurement grid we get on our data. So this solar disk imager is a HD imager. You can see the first breadboard. We had the first light of the instrument a few weeks ago in the lab. So this is the first breadboard of it. The top part, where the optics is, has not yet been installed because we're still doing some testing on the type of mirror to use. So that's for the pointing aspect. Now, since we're using this type of imager, why not trying to get also scientific data out of it by making it an hyperspectral imager? And to do that, we're using a mosaic of filter, which is directly deposited on the focal plane array of the sensor. So if you look at the focal plane array, you have actually a 4 by 4 little mosaic, which means that from a full high definition image, you can split it into 16 low resolution image at very specific filter with very specific filter response. So the filters covers 590 to 860 nanometers. I have represented their response here in the plot. And if you look at a transmission of the atmosphere at about 12 kilometers in this case, you can get information about oxygen, so pressure, water vapor, aerosols. So that's what we get as secondary data output from this HSDI instrument. And once we get the data, we are reconstructing some transmittance profile of each of the filter channels. So we'll have 16 transmittance profile, which consist of the L1 data for this instrument. The second instrument is the high resolution spectrometer. We don't have the space for an FTIR, and we need a high resolving power. So the technology we're using is that of thermal infrared laser heterodyne spectrometry. which we have further miniaturized using hollow waveguide hybrid integration. So the full instrument is is given on this CAD. It's about 10 by 10 centimeters. You have the front telescope taking the radiance in. The optical breadboard is actually that part, which is further shown here, and which is currently being assembled in the lab for our first breadboard. So this instrument, as you can see the size from the fingers here, it's about 4 by 6 centimeter, and it still maintains a resolving power of about 100,000 10 microns. So we're still able to resolve some Gaussian lines at low pressure. The price you have to pay is the spectral coverage. You have only access to a fairly narrow spectral window of 1 or 2 wave numbers. So here what we've done is that using a simulator and the typical diagnostics from the optimum estimation, we could determine what are the micro windows, combined micro windows we need to fulfill our mission objectives, and we came up with 3 narrow window which are given in the back here. So we will embark 3 Aeroses onto a single spacecraft. Because they are so small, you can actually functionalize to a specific narrow window and then take as many as you want to build up your spectral capability. This is what it looks like in terms of simulated L0 and L1 data. So from the 3 Aeroses, we get, throughout one occultation, of course, we get 6 spectra because there is a phase-sensitive detection, so we have in-phase and quadrature signal. So then we can calibrate in frequency those data to produce the calibrated transmittance across the occultation event. I didn't have space to put all the data, so you have only from high to low showing up. Now, we've got our L1 data for HSDI and for the IROS instruments. So in terms of retrieval scheme, we are very innovative with the instruments. These instruments are brand new, they've never flown before. But on the retrieval scheme, we are fairly conservative, and we've been using some existing tools which are being developed over the years, and we're working with Anu Dudia at Oxford on this. We're using the retrieval scheme developed for MIPAS, the MIPAS orbital retrieval using sequential estimation. At the heart of it is the radiative forward model, RFM, and as I say, used operationally for MIPAS and IASB. The updates we've made for this mission is first working in transmittance rather than emission. And second, we have changed the code so that it can deal with broadband filters rather than fully resolved spectral information to cope with the HSDI filter channels. So we will take all our measurement data, L1 level, on the measurement grid and map that into the retrieval space on a grid of 5 by 60 kilometers with a 1 kilometer vertical spacing, as well as all the diagnostics optimum estimation provides. So here, this is the run we've made with the simulator. It has not yet been optimized in terms of sequence, the sequential way we do it, but we inject the L1 data into the code, from which we retrieve a profile of temperature, pressure, water, and aerosol extension. And then whenever appropriate, these outputs are taken as a priori for the second sequence, where we ingest the L1 high-res data, so the 3 micro channel from the spectrometer, and produce the full final data product of this species. This is how it looks from a simulation on one occultation. I took the worst case ever, which means an equinox solar occultation where the apparent ascent-descent rate of the spacecraft is the fastest, therefore the lowest vertical resolution. So top row is the profile of the product, the species. The second row is the error outputted from the optimum estimation fit retrieval. And the last one is a vertical resolution from the full width of the averaging kernels. I also marked the green and orange lines, which shows the target and threshold requirement for the mission. So what we see here, we're pretty good where we want it to be good, which means the tropical UTLS, and the uncertainty starts to increase as the atmosphere becomes more opaque at lower altitude, and also at high in the stratosphere when the absorption from the species is becoming tenuous. So that's where we are. This is the platform which will integrate everything. I don't have much time to talk about it, but it's essentially a 6U platform. This thing is extremely small. We have a 3D printed model. This is 20 by 20 by 30. It's almost like a big shoebox. It's very small and integrate everything, including platform systems. Now, we have a problem. We have been implementing for about 18 months, and a few months ago we became aware that we could not deliver this within the budget. And so we're looking at solution. So all the teams have been scratching their heads. What can we do? How can we work with this? So what we are coming up now is on a rescoping exercise where we will first start with a CubeMap Pathfinder. So the objective of the Pathfinder is to first assess the scientific quality of the data so that we can have firm evidence that all these systems is providing the right scientific data, then extrapolate to a full-blown CubeMap mission, and also as part of that we will assess how CubeSats are suitable for this type of demanding scientific application. So in terms of the rescoping, it means we maintain all the original requirement of the instrument. We haven't changed that at all. But we will have a first step where we have only one spacecraft and one of each instrument on board for the initial scientific assessment. We will use an opportunistic launch rather than a dedicated one, which means we're likely to have a sun-synchronous orbit, which means rather than tropics, we will have a coverage which will mid-latitude and high latitude. And last, we will use the prototype processor rather than the full operational processor to generate the assessment. So that's what we're currently all putting up for as a proposal to carry on with the mission, and that's currently where we are. Okay, my last slide is a general view of this concept. So the idea here is that, and I want to insist on, is the pioneering aspect of it. So we wanted to start developing more solar limb solar occultation within Europe. All the great mission comes from Canada and the US in terms of limb solar occultation. So developing that within Europe, as well as developing the constellation aspect, which is potentially a game changer. We also have developed some really new miniaturized scientific instruments, which enables the use of CubeSats and demonstrating the use of CubeSat for scientific missions. So in terms of forward look, the thinking behind the mission is that it's a fairly versatile system. As I said, the instrument can be functionalized and you can target in any narrow window you're interested in the thermal infrared. So you can actually very quickly put together a system which is suited for a wide range of mission objective and have a system that you can launch fairly quickly at a fairly low cost. And you have actually, I think, a transformative system in terms of getting limb sending composition of the atmosphere and scaling up, of course. So that was me. Last word, I would like to thank all the people working on this. It's a large team. It's a very interesting project. It's difficult to do something which is radically new. So I really want to thank all these people who have been working hard. And I thank you as well for listening. Thank you.